You've been introduced to the algebraic definitions of dot product and cross product. The algebraic definition of dot product is multiplication of each slot and then the sum of those products. The algebraic description of the cross product is kind of a calculation with determinants that you have to practice to do well quickly. But you also know that they have geometric interpretations. And the geometric interpretation of dot product and cross product are kind of similar. A dot B is mag A mag B cos theta. A cross B is mag A mag B sine theta. Oh, but it's not A cross B. It's the magnitude of A cross B. So there's a kind of similarity between these two, and we've proved the dot product geometric representation in class. Let's look at the representation for the cross product, show you why that's true. That involves a kind of long organization of multiplications. So let's prove that the mag of A cross B is mag A mag B sine theta. Notice that the angle between A and B is always between 0 and 180. We can take it that way. So the sine of theta is always positive. And if we show that the square of both sides are equal, then we can apply the square root to both sides, and we get the result that we're looking for. But this square of magnitudes allows us to use the dot product property. The square of a magnitude is a vector dotted with itself. And we can also use the dot product property that defines cosine as the dot product of two vectors divided by the product of their magnitudes. So this allows us to replace sine squared. Let's look at what this looks like. So we understand that the magnitude of A cross B represents the area of a parallelogram. The base is the magnitude of B, and the height is the magnitude of A times the sine of theta. So let's examine mag A squared, mag B squared, sine squared theta. Replace sine squared with 1 minus cosine squared. Replace cosine squared with A dot B over mag A mag B squared. And distribute. So now our expression is mag A squared mag B squared minus A dot B squared. And the properties of dot product say that's A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared minus A1 B1 plus A2 B2 plus A3 B3 squared. Notice that this consists of 9 terms twice. 9 terms positive, and then 9 terms subtracted. So let's organize these nicely. A nice way to organize things is in a table. So when I distribute the first product of 3 terms times 3 terms, excuse me, I'm going to create these 9 terms here. You can examine them and make sure that I've accounted for everything. And when I square this expression, 3 terms times 3 terms, I create these 3 terms that I organize here in a table. Each one of them is preceded by a minus sign. A1 B1 times A1 B1 is A1 squared B1 squared. A1 B1 times A2 B2 is A1 B1 A2 B2. Now it seems like a lot of writing, but we recognize right away that some of these things are going to be canceling each other out. So let's cancel and organize. A1 squared A B1 squared, add and subtract. A2 squared B2 squared, add and subtract. A3 squared B3 squared, add and subtract. Now we have 12 terms remaining, but that's not the end of our organization. because among these subtractions, we notice that we have pairs of terms, each appearing twice. So let's look more closely at these pairs and how we could organize them. If we take these two terms, a2, b2, a3, b3, and combine them into one, we can write them with a2 squared, b3 squared, a3 squared, b2 squared, and write one perfect square. So we organize this. And this expression appears twice. So I could precede this with a -2. Notice that this is equal to a2b3 minus a3b2 squared. I've used up this term here. Now let's work on the next pairs. I'm going to take a3b1 squared a1b3 squared and combine the a1b1, a3b3 that appears twice. Bring that to the middle. Precede it with a -2. And this expression is a1 e3 minus a3b1 quantity squared. So I now used up those pairs. The last four terms here are going to combine into a third perfect square. So I have a1 squared b2 squared. I can subtract two copies of a1 b1, a2 b2. With the correct coefficient. Followed by a2 squared b1 squared. And this becomes a1 b2 minus a2 b1 quantity squared. Now if we organize these in the form of the magnitude of a matrix, notice that we have the square of a2b3 minus a3b2 right here. This is the square. I can introduce a minus sign of a1b3 minus a3b1. And the third term is the square of a1b2 minus a2b1. So these three expressions are exactly what I would get if someone asked me to take the magnitude of this matrix. I'm sorry, of this vector. Now erase the clutter and recognize that that vector is the cross product of A and B. So now we've basically finished. Magnitude of A cross B squared. So mag A squared, mag B squared. Sine squared theta is equal to mag A cross B squared, taking the square root of both sides. Mag A, mag B, sine theta is equal to mag A cross B. This is not a proof that you need to reproduce right now, but I want you to have confidence that this geometric representation of the cross product is meaningful and true.